with our discussion on the mechanical properties of solids by starting off this video with the term known as elasticity. Now, you are quite familiar with this term right from the old days because anything that the property of the body which allows the body to recover its original configuration, that is the shape and the size, even after it has been applied upon by an external force, and upon the removal of that external force it tends to get back to its original form, original configuration, that is shape and size, and that is what we term as elasticity. Now, most of the bodies, just like in case of rubber, in case of say various other the cushions that you use, most of them they have these elastic or elastic characters. Now, the bodies which do not show this elastic property, that is when they do not return back to their shape. So let me just write it for you over here, that regaining of shape, regaining the configuration after the removal of the external force that is being applied. A certain force was applied, it changed the shape, but then the body regained its shape. But there is also another term where associated with bodies which do not regain their shape, and that is what we term as plasticity, and the bodies are known as plastics. So what is plasticity? Well, that's the reverse of elasticity, where the bodies are not regaining their shape. So it's not regaining the shape and size upon removal of the external force. Now, you may take the example of any plastic object that you come across in your day-to-day life. Even the clay, the wet clay, that also has a plastic character where you can shape it as you like and it does not return back to its original configuration that it had previously. So what is the reason behind this elastic property, and what is the reason, and that will also give you the reason behind the plastic property? Well, if you go on to the variation of the potential energy curve that we had discussed in the previous video, where an object tends to remain in the least possible energy state. So in that case, the molecular range with respect to the molecular distance, intermolecular distance or interatomic distance, we had the variation of the potential and it was somewhat like this, and this was the least energy that we obtained, where we said that let this point be P and this point be A, and with those with those points, what we get is that this is the minimum potential energy at the point P that we are getting. This is the U and this is the R, U versus R curve, and OA is the intermolecular or interatomic separation, where the molecules or the atoms, they tend to remain in the least possible energy state, and it is a tendency of a body to remain in its least possible energy state. Well, what about the case when they are compressed or expanded? Now let us take the example where it is expanded to some extent. Its energy because it's expanded, so the distance is increasing to that point B. So now the distance is OB, and that point corresponding to that in the on the energy line is P1. While on compression, let's say it is compressed and the compression is OC, and thus we have the corresponding energy point to be P2. Now this tells us that the energy is P1 and P2 that we see over there, they are greater than the value P, and as a result of that, the body which always tends to remain in the least energy state will restore itself to that position or that point P or that distance OA. So that is the reason behind this elastic property. Now, any force that is involved or that is presented by the body itself in order to restore itself back into its original shape is what we term as the restoring force. So there is a restoring force which is the intrinsic part or intrinsic property of the body, which allows it to, that's the case, that's the difference behind the elastic body and the plastic body. The elastic body has a restoring force which allows it to get back to its initial shape or initial form, whereas there is no such restoring force in case of plastic objects, and that is the reason why they do not get back to the initial states, and they are happy to stay in the state as they have been subjected to. Now let us consider some terms which are associated with the with the elasticity and the plasticity, uh, such as in case of this being stress. Now the stress is the force which is applied per unit area and therefore has the dimension of pressure, and the unit is obviously Newton per meter squared. That is what the stress is all about. It's more or less for an elastic body, the stress is the restoring force per unit area. Now we have various forms of the stress. Suppose we have a surface area and a force is being applied normally on that area. So this is known as the normal stress. Force acting normally. And then we have the tangential stress, which is acted upon tangentially along the surface, the area being A, the force being along the area. And then finally we can have the other way around, which is partially normal and partially tangential. This is tangential, where we apply a certain force at a certain angle, say like this. Then it will have two components, one being the normal component, taking this angle to be theta with respect to the horizontal or with respect to the surface. We have the f cos theta to be acting along this direction and f sin theta to be acting normally. So it's a combination of both the tangential as well as the normal forces or normal stress. Now the normal stress is of two types. It can be compressional when it is trying to compress or decrease the length as well as the area or the volume of the body, while there is another stress called the tensile stress. The tensile stress results in the increase in length or volume of the body. So this can be further subdivided or subcategorized into the compressional and the tensile. So that's more or less about the stress. Now let's move over to the other type of term that we usually come across, which is known as strain. Now, whenever there is a deforming force which is acted upon on an object, a given body, and the body has certain elastic property, but there is, for that momentary amount of time that the force is being acted upon, there's a relative change. Let me use another ink for that. There's a relative change in the configuration due to this application of the deforming force, and this relative change in configuration is what we term as strain that is acting upon the body. Now the strain when we say relative change, means we are relating the change with respect to the initial configuration. That means we can consider the, suppose, let's categorize and you will understand what it's all about. So if we are considering the relative uh, change in terms of length, then we come across the longitudinal strain. Now, what do you mean by longitudinal strain? If we are considering an object, suppose, which has the length to be its prime feature. So this is supposedly an elastic band that we are considering hung from a rigid support, and we are applying a certain force, or we probably are using a certain weight which is extending the object. So we extend it. We probably use a certain weight in order to extend that object. So we are extending that object through a certain weight, and the initial length supposedly was L, and the extended length is, suppose, delta L or del L. Then we have the relation or the longitudinal strain to be equal to the ratio or the relative change as we know it. So the longitudinal strain in this case is equal to the change in length per the unit initial length that was there. We also have the lateral strain. In case of the lateral strain, what happens is that the object is expanded or extended laterally, that means sideways, as a result of which we observe the change in its sideways length with respect to any external force that is being applied. So suppose we have a cylindrical object over here, and it is hung from a certain rigid support as we considered earlier. This is a cylindrical object, elastic in nature, and it was extended, as a result of which it got constricted along its diameter. As a result of that, the new shape that we get due to the force in the downward direction is somewhat like this. So this results in a new length which is of a reduced diameter as opposed to the initial diameter. Let this diameter be d, and the change in diameter being equal to, let us say, del D. So these two have changed the diameter, the sum of these two actually. If we add both of them, we get del D. Had I considered only a single side, that is on the right or on the left, then I would have got del R, that is a reduced radius, but we have to consider both the sides in order to get, that is why the plus of both those distances. So del D is the reduced diameter, and so this gives me the lateral strain, which is del D divided by D, the change in diameter per unit diameter. Similarly, we have the volume strain, where the entire volume of a given body is considered, and the change in volume per unit volume. So suppose we compress, suppose this is a spherical object, so let's consider the case of volume strain. Suppose we have a spherical volume and it is being compressed by certain forces which are acting on its surface and reducing it to some extent. So it's been reduced to this shape upon the application of some external forces, deforming that is. And with this change in volume, we supposedly say that this is del V, and the initial volume was V, so we have the volume strain to be del V divided by V, relative change in the volume. This was the relative change in the diameter, this was the relative change in length. So relative change in the configuration gives us the strain, and as you can see, because it's volume by volume or length by length, it has no units, no unit, it's a unitless quantity. And finally we can discuss about shearing strain or shear strain, that is, let me switch to the usual ink. So shear strain is a bit different from the others, where we are considering the tangential force or tangential uh, deformation that is taking place, which is causing it to change or deform through a certain angle from its base, which is something like this. This is the initial shape that we had, and let this body be A, B, C, D, and it was acted upon by a tangential force along this direction, and as a result of that, it has shifted the top surface, just as in case of the books that you use. In case of books, if you just drag the top surface uh, from the initial point, and the bottom surface remains in contact with the platform, that is, it may be a table or a desk or anything like that, the top surface is shifted, and the shift is through an angle theta over there. And let this be C dash and D dash. So the shift is through an angle theta. Now the shear strain, because as you know, the strain is a unitless quantity, so shear strain in this case is the angle theta. But for smaller angles, obviously we can take theta to be equal to tan theta. Small angles results in theta to be taken as tan theta or sine theta, but we are considering the length by length, so we are considering the tan theta, that is the change with respect to the initial shape. So here tan theta, as you can see from the figure, this being a right angle triangle, this one as well, so we have either we have d dash or dd prime divided by ad, or cc prime divided by cb. It's all the same. So tan theta here is equal to, let's take the other one, cc prime divided by cb or bc. Take it as you like. This gives me the shear strain, and as you know, it has no dimension and no unit as well. So that's more or less about the terms which are associated with elasticity, and also a bit of knowledge about plasticity. We'll be continuing with the ending part of this topic, that is the Hooke's law and the various coefficients that are associated with the given object, showing the elastic property. But that's for the next video. Till then, thank you for watching.